Hello everyone. So today we're going to talk about fiber optics. Fiber optics is a very important topic since it allows us to have faster information, faster transfer of information, and also higher bandwidth of communication. So with this, we could attain a higher bandwidth that is difficult to attain in electromagnetic wave. Okay? And also in this topic, we're going to discuss about the benefits, the construction, the laws involved in attaining this fiber optics, the different cables, and also the dispersion, and also the solutions about dispersion. So let's begin. So first is let's study the physical optics. So let's study what is responsible for this concept. So reflection is of course the fundamental. It is the simplest way of manipulating light is to reflect it. When light rays strike a reflective surface, such as mirror, the light waves are thrown back or reflected. By using mirrors, the direction of a light beam can be changed. Okay? Of course, we are very familiar with it because it can be observed in our everyday life. So there is a law of reflection that the angle of incidence is equal to the angle of reflection. Okay? So as pointed here, the incident here and the reflected here, which A and B is equal. Okay. So the direction of light ray can also be changed by refraction. So this is our second one, which is bending of a light rays that occurs when the light rays passes from one medium to another. Okay. So the easiest thing to remember how the refraction is that of course this is air and this has different index of refraction symbolizes by N1 and N2 is also another index of refraction. And since the light will travel into another medium, it wants to go to the fastest point. Since at this point the light is of course fast, but in this time its speed will be affected. However, since it wanted to somehow it is shortcutting because instead of passing straight line like this, it goes like this, which in a sense that decreases the distance that the light will travel. So that's just a simple analogy in order to know the characteristic of refraction. Of course, this is governed by Snell's law. Okay? So when do refraction occur? So refraction occur only when the light passes through transparent materials such as air, water, and glass. Refraction takes place at the point where two different substances come together. So refraction will only occur due to the different substances that come together, or more specifically, if there are two difference in index of refraction, or also called N. Okay. So the amount of refraction of the light of a material is usually expressed in terms of index of refraction. Okay. Since different materials has different index of it. Okay, so as you can see here, refraction happened in this case. So as I've said a while ago, the light wanted to travel into shorter distance as much as possible. That's why it is here. Okay, and when we perceive it, it may look like this. Okay, so this is also one way to study, because in ancient times, being able to know this kind of properties will help you in fishing, in catching fishes, especially if you are in the water area. Okay, so pay attention to this graph. Okay, and as can be seen here, it has two materials, different material, which makes the refraction possible. So pay attention to this critical angle, because this will be critical or important in our discussion. Okay, so the critical angle value depends upon the index refraction of the glass. Okay, now there is a question: what happens when the angle is greater than critical angle? So if greater than critical angle, this is what happened. So as you can see, you see a reflection since A is equals to B. However, the more accurate response would be total internal reflection. Okay, so when the light ray strikes the interface at an angle greater than the critical angle, the light ray does not pass through the interface into the glass. The effect is as if mirror existed at the interface. So since we're not dealing with, or the angle is greater than critical angle, as in this example, so this is what makes the total internal reflection possible. Okay. Okay. So this topic, especially this one, will be useful in the construction and also understanding the latter topic. Okay. So in the fiber optics, or in the light, you can see that light is used. So light source can be LED or laser. Okay, so this is a modulator, and this is photo detector. It is also important to consider the materials used in order to harness the speed of this one, because if your photo detector is has a slow response, it will also affect the transmission. So amplifier in order to amplify the attenuated signal, and the modulator. So the good thing about this is that if there are surrounding electromagnetic interference or radio waves, it cannot be easily affected by those interference, such as radio waves, microwaves. Okay. So this is also applicable or can be used in a fire sensor. For example, there is a smoke here. Okay, there is a smoke. Okay, so it will be passed, and the photo detector will detect that there are no laser. There must be an obstacle here, so it can be used as a fire detector. Okay, so especially if you are in the larger area. Okay, so fiber optic cable as the medium. So if you are presented here by an analog signal, which the example here is voice or video, it is converted and transferred into binary, or what we call here pulses. And then this pulses will be the one who will turn off and turn on this light source. and then this will be transmitted using the fiber optic cable. Ah. And so on up to here. Okay. So and then there is the receiver, and then converted into pulses, and then decoder, and transferred into original voice or video. Okay, so this is an example of fiber fiber optic cable as the medium. Okay, so in further understanding the concept of fiber optics, we should ask ourselves why it is better than conventional electric cables. First and foremost is the wider bandwidth. Okay, so it has this capability to transfer higher bandwidth, which is in turn higher data rate. Okay, low loss. So fiber optic cables have less signal attenuation over given distance than an equivalent length of coaxial cable. An example of this would be in electrical cables, especially if you're dealing with meters, you can have a measured attenuation, but in fiber optics, even if you're dealing with kilometer, start of kilometer or in the range of kilometer, that would be usually the start of the attenuation. Whereas in the electrical cables, usually in meter, there is attenuation that can be observed. Lightweight. So glass or plastic cables are much lighter than copper. So these are beneficial if you are dealing with the fiber optic cable. So the reason why it is lightweight, because the construction of the material would be so this is fiber optic, this is made of glass or plastic, so this one is hollow, whereas into the copper, so this is denser compared to copper, compared to the glass or plastic. Okay, in the sense that because it is hollow. Okay, small size, so usually it is in the small size due to the dispersion. Okay, later there are strategy that reducing the size would also benefit on reducing dispersion, which will be also discussed in the preceding slides. Security, so it cannot easily be topped compared to the radio waves, microwaves. Interference immunity, so it is immune to the interference such as other interferencing signal. And greater safety, so perhaps this is what I like the most, since there is a danger of electrical cables which produce shock hazard if also susceptible to the lightning strikes. Okay, so they can also be used in corrosive explosive and without the danger of sparks. So especially if you are in the sensitive areas such as nuclear, gasoline station, or other hazardous place where sparks and fire are very dangerous. Fiber optics will also one of the good things, because it lessens the probability of sparks that may cause fire. Okay, so we discussed the benefits of fiber optics. Now we're going to discuss how fiber optics works. So as you can see, the line that I've made somehow resembled in this kind of this illustration. So, critical angle. Again, we're back to the critical angle. The angle of light beam B such that its angle incidence is less than the critical angle and therefore the refraction takes place. Okay, so we discussed a while ago that um, the incidence is less than the critical angle, so that's why it is refracted. Okay, so B is considered as loss. Okay, and therefore refraction takes place. So compared to A, C, and D, so it has greater angle, which the total internal reflection takes place and the light beams are reflected off the surface of the fiber cube. So the one that made it through is C, A, and D. But the most desirable in this one would be, of course, A, since it travels into a straight path. Okay. So, and also one way to account in this concept is that some paths will be longer than others. Therefore, if multiple light rays enter at the end of the cable, they will take different paths, and so some will exit sooner and some later than others. So here we are assured that if this is a race, A would be the first, and we don't have much data about the C. Perhaps we're just going it as second. Okay. So this concept would be very important because this is the reason, or this is the foundation of the dispersion. Okay, which is undesirable in the fiber optic system. Dispersion is undesirable. Okay, so that's why in this one we do not have cone of acceptance. To make it easier to analyze, we have this cone of acceptance. So it shows that the critical angle of the cable, which is this one, sometimes referred as the acceptance angle. The acceptance angle is formed between the center axis line of the core and the line that defines the maximum point where light entering the cable will undergo total internal reflection. Meaning, if your angle is within this cone, it will be accepted. That's why it's called cone of acceptance. And outside of the cone will be the energy will be refracted and thus propagation will not occur. Okay, so the cone of acceptance defines the numerical aperture of the cable. This is a number less than 1, gives some indication of the range of angles over which a particular cable will work. So this is an example of numerical aperture in action. Okay, so given that 0.29, we are looking for this one. So it is also an important parameters that we should consider. Okay, every fiber optic cable has different numerical aperture, thus different cone of acceptance. Okay, so the portion of fiber optic cables that carries the light is made from either glass or plastic, or it can also be called silica. So the optical characteristics of glass are more superior. Of course, we would like this glass compared to plastic. However, glass is expensive and more fragile than plastic, so durability is also one of the downside. Although plastic is less expensive and more flexible, its attenuation of light is greater. So the signal integrity loses in plastic compared to glass. Also, the index of refraction of the outer cladding of N2, we're specifically pointing at this one. Cladding N2 is slightly less than the index of refraction of N1 of the core. Typical values for N1 and N2 are 1.5 and 1.4. So as you can see, N1 has a large index of refraction, this one, and this one is has lower. That's why I have this example in order for you to visualize or somehow get the concept of this refractive index. So I showed here that the highest refractive index is diamond, which of course eminent because it is made of glass or somehow has the characteristic of glass. Okay. And also as you can see, this one is N1 is much greater than N. Okay, so construction. So as seen here, we discussed this glass or plastic core, and this is the cladding. We discussed also the index of refraction between these two. Okay, so the fiber is usually called core, surrounded by a protective cladding. So cladding is also a protection. So also it has also another purpose. The cladding is also made of glass or plastic but has lower index of refraction. That's why in our previous slide, the difference between the two is just 1.5. This is 1.4. Assuming we're looking for this example. Okay. This ensures that the proper interface is achieved so that light waves remain within the core. In addition, to protect the fiber core from nicks and scratches, the cladding gives strength. Okay, so this is also importance of the cladding. So to ensure that the proper interface is achieved so that light waves will remain the core, and thus the refractive or the refraction will be lessened. Okay, or going out of this cable. So commonly this is the construction. So core, cladding, protective coating, Kevlar sleeve, and this one. This is a basic construction. Okay, so the types of fiber optic cables. The first method is by index of refraction. So in my preceding slide, you will notice this word in the name, which varies across the cross-section of the cable. The second method of classification is by the mode. So mode is also can be seen in the name, which refers to the various paths that light's ray can take in passing through the fiber. So we will discuss this, but when we say various path, this is like this. Okay, so there are various paths passing through the fiber. Okay, so at least just to give you an intuition, and later we will discuss this in depth. So step index cable. So the two ways to define index of refraction variation across a cable are the step index, the graded index, okay, and graded index. So this is the first example. The second example will be the graded index, which will be discussed in the next slide. Step index refers to the fact that there is sharply defined step in the index of refraction where the fiber core and cladding interfaces. So this sentence is defined here, okay, as can be seen here. As you can see, step index, that's one, because as you can see, this is like a step. Okay. So also this is a sharply defined step because the N1 and N2. As we've discussed a while ago regarding the index of refraction. So that's why it's called step index cable. By the way, this one is constant, this one is constant, because that's the difference between the graded index. shown in the next slide. Okay, so this is the second example. The other type of the cable has graded index. Again, we're talking about the index. So as I said a while ago, we have two, which is this index of refraction and this mode. Okay, so the other type of cable, this one. So this one can be illustrated using this one. As you can see, it's not a step and it's also not steep. So it has a smooth transition over the cladding and this one, the core. So that's the graded index cable. Okay. So cable mode. So cable mode refers to the number of paths for the light rays in the cable. So there are two classifications. So single mode, the light follows a single path through the core. So this one. And multi-mode lights takes many paths. Straight, it should be straight. Okay. So in practice, there are three commonly used types of fiber optic cable. So we discussed the index and also the mode. So this is a multi-mode step index. So remember the step index and apply the concept of multi-mode. So therefore, it has like this kind of path, and the cladding with respect to the core would be like this step. So same concept will be applied here. The step index. So multi-mode graded index. So if we're using the graded index, the one that has smooth transition between the N2 and N1. Okay. So the multi-mode step index fiber cable is widely used at short to medium distance at relatively low pulse frequency. Okay, this cable is also the easiest to make and least expensive of the fiber optic cable. This is easiest because, as you can see, the graph of N2 and N1 is like this, which somehow it does not have a smooth transition of the fiber. Okay, so this is the example. Okay, multi-mode because it has a lot of paths. So there is C, there is B, there is A, okay, and also there is dispersion. Okay, so in this one, the input pulse is like this, as we have discussed. However, the output pulse is like this, which is not what we wanted. So the reason why the output pulse is because of this one. Of course, A would be faster, so perhaps the pulse of A is here and the B is here. So A, B, and C. So they do not go or reach the end at the same time. That's why it somehow stretch the light pulses. So this is what we call dispersion. So as you can see here, dispersion is happening in this one. And this is what we do not want because it will produce error, or also when decoding signals, especially if this is 1 and this is 0, 0. So in this one, this would be 1, 1, 1. So as you can see, this one is an error. And we do not want that. Okay, kinds of dispersion. So there are lots of dispersion, and we should be able to account of this kind of dispersion. The first one is the attenuation of the light in the cable increased in duration because of different arrival times of various light rays. So stretching of the pulse is referred to as modal dispersion. This is what we see in the previous slide. So as you can see in this one. Okay, so assuming this is 1 volt after the decoded, so 1010110. So in this one, this one which is correct, but this one can also be considered as 1 1 1 1 1. As you can see, this one is wrong, this one is wrong, and this one is wrong, and that affects our data communication. There are solutions in this case. The first one is lower the frequency. Why? Because assuming if we have only 2, so we have to use this one. So input, lower the frequency, we were going to lessen the data transfer. Okay, so if you have like this as an input, the output would be, considering the dispersion, would be this one. Okay, and since we have lower frequency, assuming this one, so this one is 1, and this one is 1, and this one is 0, this one is 0. So we've accounted that it may take long, so that's why it has a low frequency. Okay, so select a cable that has so as you can see in this one, since it has lower frequency, the error will also be lessened, and this can be considered the same input. Okay, compared to this one, which has a high frequency, which also produces a lot of errors. So also the second solution would be to select a cable that has low modal dispersion. So the next one would be chromatic dispersion. So from the text itself, chromatic, color, and dispersion. So we know the concept of dispersion. This occurs when multiple wavelength lights are used, as in this case. It's in the dense wavelength division multiplexing systems, since higher light frequency travel faster than the lower light frequency, pulse stretching occurs. So this is because of the colors. That's why it's called chromatic. Okay, so of course, you know, there are different frequency between the blue, the light green, yellow green, and the red, which produces this kind of dispersion. Okay, so the next one would be polarization mode dispersion. This is a phenomenon that occurs in single mode fiber. Essentially support two orthogonal polarization along cable. Since the cable is not perfect cylinder, and because of cable distortions caused by bending, twisting, and other stresses, so polarization mode dispersion occur. So as you can see here, this is what happened in a perfect fiber. So this is because of this one, bending, twisting, and other stresses that may affect, which makes this one. And this is a delay time, and we do not want that in our digital communication system. Okay, so this is problematic, but don't worry, we have solution. Okay, so there are 3 solutions in the dispersion discussed. The first one would be using electronic dispersion compensation. So EDC uses equalization techniques to adjust the received waveform to compensate for any type of dispersion. Can be made to correct the frequency response of a circuit, but also can be designed to correct for phase and amplitude differences. So this EDC is used to correct those kinds of dispersion. Um, this is a transceiver device because um, some EDC are used for one specific error adjustment, but there is also some electronic dispersion compensation which correct multiple kinds of problems in dispersion. Okay, so you will configure this in the transmitter side in order to have somehow a training which gathers the data that will be used in the receiver side. So that is the concept of electronic dispersion compensation. So it is a compensation for the dispersion made in the fiber optic cable. So that's a good way to solve or at least lessen the dispersion happening in the system. One great idea in the next solution would be to avoid the dispersion at all, and that would be this one, single mode step index cable. So as you can see in this light source, there is no dispersion that happens since there are no multipath or multi pathways of the light source, which eliminates the modal dispersion. So it makes the core so small so that it minimizes, to reflects like this and this and this and this, like that. So by making the core so small that it has like this performance. Okay, so Einstein said that an intelligent person solves the problem, but a genius person avoids it. So this is one way of doing it, which somehow, but you cannot totally avoid it, but somehow lessen and avoid dispersion. Okay, so this one is also one of the ingenious idea to solve the dispersion. So as you can see, in this one, this is somehow predictable. Have several modes or path transmission, but they are much more orderly and predictable. So it embraces the fact that I cannot avoid the multiple pathways of the light. Therefore, if that's the case, then I'm just going to make it predictable and designing that it would go what I expected. And by that, you can see the materials is engineered to have this kind of response, and thus making it predictable. And by making it predictable, we know that the dispersion is very small compared to this one, okay, which is an ordinary and has a lot of dispersion. So that's it for my slide, for my topic, and in this video we discuss about fiber optics, and along with the parameters, formulas, concepts, dispersion, and solutions. Thank you for listening.